All right, so 2.2 notes. Yesterday, we learned about polynomial functions, but we mostly focused on quadratics, so the x squared. Today we're going to look at all the polynomials, so x squared and above. So in order for a function to be a polynomial function, we need the graph to be continuous. So we need two things for a function to be a polynomial function. First thing is our graph has to be continuous. One way to tell if our graph is continuous is if you draw the graph with a pencil without lifting the pencil from the paper. So here we see our first example on the left. This would be continuous because you would just draw the graph. You never pick your pencil up. For the second one, this is not continuous because we would have to pick our pencil up to draw it. So this is not continuous. Another feature our polynomial graph has to have is it has to be smooth. An example of it not being smooth is on the next slide. It can't have a sharp turn. So if a graph has a sharp turn or an edge, a pointy part, like here we see this has a edge to it, then it is not a polynomial function. So the two things we need our graphs of polynomials to have is it needs to be smooth and it needs to be continuous. So these are the two things we need to have in our polynomial function. So the graph has to be smooth and it has to be continuous. So our polynomial function is going to be x raised to some number. So in the last section, n was 2 because it was x squared. But now we're going to focus on higher numbers. But when we talk about n, we're talking about this exponent that x is raised to. So when n is even, the graph is similar to the graph of x squared and touches the x-axis at the x-intercept. So when n is even, our graph looks like an x squared graph. So it'll look something like that. When n is odd, the graph is similar to an x cubed graph. So our graph would look something like that, like an x cubed graph. We're going to talk about end behaviors of our graph. So where our graph is ending are our end behaviors. If n is even, our end behaviors go in the same direction. So if our leading coefficient is positive, our graph is going to end going up. If our leading coefficient is negative, our graph is going to end going down. When n is odd, our end behaviors go in opposite directions. So here we see our x cubed graph starts going down and then ends going up. If we look here, our graph is increasing, so that's how we can tell this is the positive x cubed. If we have a negative x cubed, it would go the other way. And we can see our slope here is decreasing, so this would be negative x cubed. All right, now we're going to look at some examples. So we need to sketch the graphs of g of x is equal to negative x cubed. We just said our x cubed graph looks like this. And when it's negative, we just flip it the opposite direction. So our x cubed graph is increasing, so it would look like this. If it's negative, it goes the opposite direction, so our negative x cubed graph is going to look like this. For B, here we're taking our x cubed graph and adding 1. What is this plus 1 going to do to our graph? Which direction does it shift it?
Up 1.
Up 1, perfect. So we take our x cubed graph and just shift it up 1. So instead of going through the origin, we're just going to go up 1 and go through this point. All right, for C, what does this minus 1 inside do to our graph?
It shifts it to the right one.
Perfect, shifts it to the right one. So again, instead of going through the origin, we're just going to shift to the right one and go through this point. So our graph just keeps the same shape, but we just shift it. Any questions so far? All right, next slide talks about the leading coefficient test. So when n is odd, we know that our end behavior of our graph goes in opposite directions. When describing our opposite directions, we can see that where it's going down is our left part of the graph. So we would say this is falling because it's going down, left, and then the part going up is our right side of our graph, so this is rising, right. So that's how we would describe our end behavior. So in a polynomial function, when our n is odd, so that means it can be x raised to the third power, x raised to the fifth power, x raised to the seventh power. When our leading coefficient is positive, it's always going to have these end behaviors. It's always going to start falling left and end rising right. When our leading coefficient is negative, so that number that's being multiplied to our highest x power, if that's negative, it just flips. So instead of falling left and rising right, we are rising left and falling right. So when it's negative, we just flip it. When n is even, we know that our end behaviors are going to go in the same direction. So if our leading coefficient is positive, they are going to end going up. If it's negative, they end going down. So we would just say rises to the left and right or falls to the left and right. All right, so here we have an example. It says use the leading coefficient test to describe the right hand and left hand behavior of the graph. So we're only looking at our leading coefficient, our highest x term. So we're looking at this negative x cubed. What does the cubed part tell us about our graph? Is it going to go in the same direction or opposite directions?
Opposite.
Opposite. So it's odd. So it goes in opposite directions. What does this negative tell us?
Would it be rising, left, falling, right?
So first
Rising, left,
thing,
falling, right? Or no?
first thing we can do is draw our x cubed graph. It looks like this, and we know that it has a positive slope. But here, we're going to have a negative slope because our leading coefficient is negative, so we need to make it go the other way. So it's going to go this way.
Yeah, exactly.
So this rises to the left or right?
Rises left
So rises left.
and then falls right.
Perfect. So in my opinion, it always helps when you draw it, just so you can see which direction you're going. Any questions here?
These have nothing to do with vertex or anything like that, right?
Right. So vertex only applies with your quadratic graph, so it's x squared. All right, next we're looking for real zeros of our polynomial functions. So back in chapter 1, we found the zeros of a function. We're doing the same thing here. Finding the zero, finding the solution, finding the x-intercept, they all mean the same thing. All of these mean where the graph crosses the x-axis. And our graph crosses the x-axis when y is equal to 0. Or we could say when f of x is equal to 0, because f of x is the same thing as y, just written fancier. And sometimes to find when y is equal to 0, we need to factor our function. All right, let's look at our next example. Find all real zeros of f of x is equal to x cubed minus x squared minus 2x. So the first thing we need to do is make sure that this is written in standard form. Is this written in standard form?
No. Or yes?
Yes.
Because,
Yeah, it is, because we have our highest variable first, we have our x cubed first, then our x squared, then our x. So perfect, it's in standard form already, we don't need to move anything around. Next, let's find, it doesn't ask us for this, but let's find our end behaviors of this graph. So we're looking at our highest x, so this is our x cubed. What do we know about our end behaviors if we have an x cubed graph?
They're going to go in opposite directions.
Perfect, they go in opposite directions because it's odd. And then is our graph going to look like this or like this?
The top one.
The top one. It's positive, so it goes in the increasing direction. So what do we know about our end behaviors? What can we say?
Falls left, rises right.
Perfect. Falls left, rises right. Now let's find our real zeros of our graph. So the zeros are going to tell us where our graph crosses the x-axis. To find the zeros, we just change our y, or our f of x, to be 0. What do we need to do first to find our zeros here? We're going to have to factor, but what can we do before we factor? Do we have anything in common between the three of these terms?
we have 1x.
We have an x, so we can pull out an x. So then we're left with x squared minus x minus 2. And now we can factor. So we just keep that x on the outside. What are two factors of negative 2 that add up to give us negative 1?
Negative 2 and 1.
Perfect, negative 2 and 1. So we have x plus 1 and x minus 2. And then we just set all three parts equal to 0. So we have x is equal to 0, don't have to do anything there. X plus 1 is equal to 0, and x minus 2 is equal to 0. And then we just have to solve for x. So we subtract 1 on both sides here. We get x is equal to negative 1. Add 2 to both sides. X is equal to 2. So these are our three real zeros here. So this is the 3 points that our graph is going to cross the x-axis. If we look at our highest exponent, we see that it's x cubed. Our highest exponent is going to tell us how many zeros we have. So if we get less than 3 zeros, we know we did something wrong. So that highest exponent tells us how many zeros we're going to get. Any questions here? The next 3 slides are just like the solution to the problem we did. So it just says that It starts by finding the end behavior, then they find the zeros, and then they just plot extra points to see what the graph is going to do.